Okay. So title of my talk is How Computational Models Can Facilitate Robust Theory Development, Testing, Implementation in Organizational Science. The implementation is one slide, a small thing I don't do much of, but I wanted to bring it up. This is more about robust. This isn't about replicability as much, and it's not about reproducibility. It is more the issue of robustness. An overview of what I'm doing. Because of this issue of robust science, Harking seems to have come up, and I'm going to use the Harking example as a potential problem, though really I'm going to say, no, there's a larger problem that's much more interesting. I'm then going to talk about how computational models can help us with that problem, and then circle back to Harking. So, problem-facing science. I'm going to also, like some of the other speakers, kind of go to the high road. The problem-facing science is understanding nature so as to predict and, if possible, to control. That's what we're trying to do. Most useful if the understandings are comprehensive, parsimonious, accurate, clear. Where clear means is the issue that science is social construction requiring symbolic interaction among the scientists, and communicating complex theories and ideas is difficult and requires considerable effort on the sender and receiver, which is why I clapped at Mika. Is that Micah? How do you say your name? Maka. I knew I was going to get it wrong. To me, that's a big issue of the communication is about make sure we disseminate well. That's an issue for me. That is one of the reasons I worry about the Harking cures. Science is, sometimes I ask my audience this, but I'm just going to tell you, science is systematic observation. Actually, that's just the empirical part. It is also pattern recognition and representation. That's the theory part. Theory largely derives from observations. Patterns are recognized, explanations for the patterns are described. That's what we in science call inductive. Going to Peter's, that's not what philosophy calls inductive. Philosophy has a different meanings for inductive than deductive, but science, this is what we tend to call inductive. Theory can be used to generate patterns where we are doing extrapolations or interpolations of, oh, then this should be the case, and that's what hypothesizing is, and that's deductive. Observations are systematic to the extent that they can be used to see the patterns and eliminate alternative explanations for them. So that's what science is. Hopefully, people are on the same page at this point. The acute problem. Lots of weak, narrow, and imprecise theories, as Steve pointed out. Conceptual parsimony is generally not to be had. Accuracy and comprehensiveness, they're all low in general with our theories. Therefore, they're not very useful. Why is this? Poor understanding of what systematic means. Poor representations of theories. It's easy to confirm weak theories with inexact empirical designs. So, an inexacting empirical design example. A student researcher asked 2,000 MTurk workers to complete 15 measures unsystematically chosen from a compendium of measures at time 1 and 15 different measures at time 2. Tells a story, i.e. theorizes regarding some subset of the time 1 measures found to significantly relate to some of the time 2 measures. What is the alternative explanation for any of the findings that the person has? Chance. Maybe there's nothing going on. Anybody recognize this example? This is from Hollenbeck and Wrights. It's their egregious Harking example. I have a problem with this example. Specifically, oh, by the way, just so we're clear, specifically, Harking might obscure the degree to which one is capitalizing on chance. Harking, by the way, is shorthand for sharking, which is secretly harking, hypothesizing after results are known. Tharking, this has come up earlier, is transparent harking, and that's assumed fine. Okay, so when I say harking, and I think when we say harking, what we're saying is it's sharking that we think is bad. But so here's some of my problems. So they went on to say, the student converts some of the IVs and DVs to mediators based on the results and the post hoc narrative, and then presents the results as an a priori causal model that is written up and published in a top journal. Sinner. Problems with the example. So first of all, this is really a nit, but it drives me crazy. The student converts some IVs and DVs to mediators. So IV means independent variable. It is an exogenous manipulated variable in an experiment. It is not a passively observed variable as it was in that study. And a DV is a dependent variable that only can be used to label what is being looked at as the outcome of the experiment. Using IV and DV this way is wrong. My point of that is labels only should be used with experiments. It reflects the role of the experiment, not the analysis. And language, as it turns out, gets us messed up. And here we should know better, and we should be precise. We have precise what these mean. We misuse it all the time. When I'm in a good mood, I like, yeah, whatever. It does. When I'm in Colorado, sometimes. Where am I? Mediator is a label for a causal variable and the role in an analysis. Mediator drives me. That's another one that drives me crazy. It's very confusing because a mediator, most of the time when you say, wow, I found this mediator, that means you said X causes the mediator, which causes Y, and yet you never say the word cause because you know you can't because you just have passively observed data and you can't be saying that, and yet you use the word mediator because that was a mediator in my statistical test. Drives me crazy. Lots of things drive me crazy. The ambiguity of language is the issue here. Most theories are verbal and natural language only, and we have a lot of trouble understanding what people said, which I think you also said that one too. Is I have read people who have interpreted. I have gotten those reviews where Vancouver said this, and you're wrong, and I know I've had to come back. I know Vancouver. He said that. It is amazing. So more problems with this example. So he goes on. They go on to say the study attracts a great deal of attention because its novelty and counterintuitive nature, and several other researcher teams tried to replicate the findings. None are able to do so. A meta-analytic follow-up provides the best true estimate, near zero, of all the parameters, and the field eventually abandons the model and the field moves on. Okay, so there's a few things there I'm going to let go on a slide, but it's much more likely that the meta-analysis would have validated the effects found. Much more likely. Cronbach's crud factor, and correct me if I think this is Cronbach. Hopefully there's somebody else in the room who knows this, whether it's Cronbach, and will give me a site. But when I was in grad school, there's Cronbach's crud factor. Everything is related to everything. So the idea that that was zero, that this is near zero, and that therefore they wouldn't have found anything with the meta, no, they would have found something because everything's related to everything. So, is it chance or is it replicable? So though chance is possible whenever stochastic processes are involved, personally, I think it's likely rarely true in practice. Critically, what's really the issue here is replicating a non-zero effect does not validate the explanation of the effect. And usually that's what we're trying to sell. Some might worry about unmeasured third variables and alternative causes, pairs of constructs. If that's, oh, wow, you're missing third variables. Some might worry about reverse causality. Not enough because we think longitudinal design addresses that. So there was a time 1 and time 2, and they measured the x's at time 1 and the y's at time 2. And so, no, you can't have reverse causality. No, that design does nothing for you in terms of time precedence. And I would like to do a survey. I'm guessing half of the people in our field don't know that's true. They don't know that that time order doesn't make any difference. Some might question the linearity and stability assumptions needed. I almost never see these kinds of assumptions talked about as assumptions that are needed to be met to be doing path analyses. Some might question the logic of the arguments. I'm bolding this because this is where I'm going to focus. The logic of the argument is made for the explanation proffered. The logic of the argument should be the first focus. Tharking, which holds the theory to the end, obscures the argument. I'm not a fan of Tharking when it's put into discussion, because people don't even know what the argument is. And then this is part of the empirical question. Are they much more likely to go, oh, there's the explanation, there it was in the end, and therefore they're more likely to believe it? Or are they going to never even get to the end and not even hear what it is? I don't know, and I worry about if you put it in the end, if that's the right thing to do. The logic of the argument, though, that's the issue here. That's one of the issues. The level of explanation of the theory, first of all, I've got to make a distinction. So there's cover law theories. These are the kinds that Steve would not call a theory. I don't like to call them theories, but some will call them theories. Cover law theories are descriptions of a set of relationships argued by previous research findings of the relationships. They're narrow, they're imprecise, they're low on parsimony, they're generally unhelpful. If you want to label them a theory, that's how you define your theory, go for it. That's only one kind. The kind I'm much more interested in, better theory, is the theory that describes the mechanisms and processes thought responsible for the relationships predicted. And one of the things we need about those theories is scientific plausibility of the explanation. Have similar mechanisms be found elsewhere? Theory is analogy. Is there an analogy? Counterintuitive findings may be okay if they are not counterdeliberative. So if you're like, oh, that surprises me, let me think about it. And if you think about it and you go, well, that still surprises me, that still doesn't make sense, then that's bad too. Can the mechanisms described produce the relationships observed? That seems like a question you might ask about a theory. Is the theory internally consistent? Does it really make sense? So I will read articles and I'll be reading the theory and I'll just say, this doesn't make sense. It seems like what you're going to get is contradictory. It's not consistent. Can the phenomenon, the real question often is, can the phenomenon presumably explained by the theory be derived from the constellation of proposed mechanisms working together as described? The challenge of assessing the logic of theories, accepting that the problem space for our science includes complex systems interacting with or nested within complex systems in complex environments over time, and key properties of those systems or their processes are often obscured from observation, they're latent. Accepting the capacities to represent ideas about how these systems and processes are limited in the human mind, the conclusion is we need a support mechanism to help us think this stuff through. To what extent, what external support is used when data is complex? I'm going to open that. What do we use to help us understand data? What do we use? What? Data analysis, statistical analysis. Okay? What external support could we use if theory is complicated? Steve's going to answer that one too.
A tool that allows you to evaluate your theory and its mechanism.
A computational model. So, and let me just this issue of accepting the limited capacities, I'm going to throw up my favorite quote, HINTZMAN, 1990. To have one's hunches about how a simple combination of processes will behave repeatedly dashed by one's own computer program is a humbling experience that no experimental psychologist should miss. Here's the Vancouver analogy. Computational models are to theory what statistical analysis are to data. We need help understanding how these processes will play out as we talk about complex, nested systems and dynamics in particular. So, computational modeling to the rescue. Computational model A encourages a process view of phenomenon and a more systems or holistic approach. I am going to qualify that. That depends on the particular approach you use. So sometimes the formal models aren't going to necessarily do this, but some do. It increases or potentially increases theoretical parsimony by vetting theories, removing the unworkables, by encouraging integration and exposing overlap. It increases precision and transparency, less ambiguity of concepts and explanations. I have to qualify that. If you look at the math and say, okay, I don't remember math, then it won't help. But otherwise, specific predictions compared to natural language theories. I like this quote too. Mathematics is the language with which God has written the universe, which is what we usually paraphrase as mathematics is the language of science. That's from Galileo. I was asked recently, why did I get into computational models? This is the answer. Math is the language of science, and psychology isn't very mathematic, and it should be. Assures internal consistency and logical consistency. Does the model work? Does it account for the phenomenon it's claimed to explain? And simulations of the model can lead to identifying methodological challenges and how to pit theories and new predictions or insights, and perhaps what's the optimal settings. That's the implementation part I'm going to talk about in a minute or a little bit later. In fact, what I'm going to do is I'm going to focus on some examples that highlight these highlighted parts of this contributions. And that's where you'll get to fall asleep. Okay, so encouraging theoretical parsimony towards a cumulative science is that's what it would be very much more efficient if we did. So a paper just came out last year, showed the overlap between social cognitive theory and control theory views of self-regulation. Bandura and I have been arguing for years to help resolve this, and I hope as the final chapter is, here's what it is that I've been saying, and by the way, this is a lot like what you've been saying. I have no illusions that he's going to go, oh yeah, no, that is what I've been saying. But hopefully the others will. Vancouver, Weinhardt, Schmidt, so the green means, by the way, it's published, show that the same structure, a mechanism used to account for goal striving, could account for goal choice. The mechanism has many names. It's a negative feedback loop of a specific kind. Control system is a common name for it. Cybernetic system is a common name for it. It's because of the strategy people. Policy is what Forrester calls it. I call it a regulatory agent because I think there isn't enough words for it yet. Actually, that's just a part of it. I'm going to show you this model. I'm not going to explain it. I'm just going to talk about a few little features of it. So here is the model. And the thing about these white ones, that's the goal-striving mechanisms. And these little circles, that's the agent. And what you see is there's the agent over and over again. And these colored ones are particular agents that help us understand choice, which is kind of thinking. So this is really about acting, and this is about thinking. And the really cool point I'm trying to make here is, although that parsimony is not the word that jumps to your head when you look at that model, that is conceptually parsimonious. I mean, to me, it's beautifully parsimonious. It's a beautiful thing. More encouraging to theoretical parsimony. We then followed up showing that the structure was identical to the one used in connectionist models of learning and how to fit them together with regulatory goal processes, in particular the delta learning rule. Now, one of the things I've been trying to do in my career is get us to have some paradigms. I would argue that connectionist modeling is a paradigm psychology has. With this paper, we are connecting the self-regulatory paradigm with that paradigm. And that is what the model looks like. Those colored ones are the mechanisms that describe two things that this system is learning. And you can see clearly as day that they are the same structure. Trust me, they're the same structure, basically. So that's cool, right? It encourages process explanations. So I'm going to cite a few other people. It's going to be rare for this talk. Cumulative effects of small prejudices. Martel, Lane, and Emmerich. See, I didn't even try to pronounce names. On the multiplying effects of slight differences in the probability of being promoted substantially affect the number of women in top management positions. So small effects propagate through a system and create a fairly large effect. Zucker, how do you say his name? Zicker, on how faking good, that relatively few people might fake good on personality selection tests, but they're more likely to be selected, and so it doesn't adversely affect the validities, but it does change the nature of the people who are working in your organization. Norm formation and maintenance. So Perlow and Repping on the dynamics of silencing conflict between self-reinforcing norms within organizations. That's kind of more strategy. I don't know if you guys read this. These are more strategy people. More encouraging. Vancouver and Gonzalez Vallejo, colleague of mine, show how a combination of the same structure could account for prospect theory's curves and provides an explanation for a descriptive theory. So prospect theory is a descriptive theory, describes this curve. It has a verbal explanation. We have a different one. I have not tried to publish this. That's why it's blue, because there's going to be a whole field that's going to come down on us when we try to do this, and we are not ready to do that yet. This is one that Mo and I and a student of mine have under review about Locke and Latham's motivational hub, where we turn that theory that is static with a little bit of wanting to be dynamic into a dynamic theory, and we reveal the temporary effect of assigned difficult goals if the theory, as it seems like they're describing it, is correct. In other words, their theory seems to say, actually, this isn't going to last. And their theory is based a lot on empirical work, so it doesn't seem like this is going to last. We learned lots of interesting things doing that paper. Yes, that's probably not over. So another student, we built a model of new goal development to fit against data demonstrating the same thing, which is, so a big question in goals is, where do we get goals from? And so we have a computational model about how it is we get goals, and we have this data set we use to show that that model is reasonable. Haven't tried to publish that one either because it's really complicated. Scherbaum and Vancouver showed how, I'm still on process explanation, showed how goal discrepancies might be created. Bandura merely argued that humans do this, and we went ahead and confirmed this with a new data set. So that's what the italics means, we have data as opposed to using other people's data. Guy et al., we showed how self-set goal levels might be determined. This is under review. We modeled the protocol and the data. I'm going to just come clean here. What we did here is actually, these are Australian. I went to Australia, and they were talking about these various studies we did, and I sat down for the first 3 days that I was there and created computational models that would help explain the data that these people were finding. Which came first, the data or the theory? In that case, the data did. Maybe. I mean, I was like, oh, as they're talking about the paradigm, I'm working out that model in my head, and I start creating the thing. So one of my big points about Harking is you don't know what comes first, the data or the theory. It's all circular, and this notion of thinking you know the linearity of it ever is a fallacy. Vancouver et al., we examined process explanations of non-normal distribution, performance distributions. One of the main reasons we were doing that is because the people who were talking about this were saying there's this person-centered explanation, there's these star people, and we showed how that does not hold up. It really doesn't seem possible. What does seem much more reasonable is an interactional one, and we fit this to existing data, though I'm saying here not very diagnostic. It's not. I mean, that model needs to be tested much more rigorously. Most of the models need to be tested much more rigorously. When we make a model and we fit it to data, we are not done. The field is not done. I'm not making that. I want to make sure everyone knows that's not the case. Pitting theories, favorite thing. So what Vancouver and student of mine, Scherbaum, we built 2 computational models of self-regulation, one regulated behavior and the other one regulated perceptions, and used the models to find a method that would empirically separate the models. We also reported the results of the study of that method, of that paper. Self-regulation perception was a clear winner. Had a hard time getting this published, by the way, because everyone said, oh, you set it up so that would be the winner. And I mean, yes, I knew that would be the winner because the other one was stupid, but anyway, that's what you pit these. That's what you do. You pit these against each other. Built 4 models to explain the existing set of findings of the goal gradient effect. So the goal gradient effect, control theory is another word for what I deal with. Control theory says, here's this goal, and as I get closer to as the discrepancy gets smaller, I'm either going to be, my output is going to be the same, it's either on or off, or it's going to get weaker as I get closer to the goal. The goal gradient argues the opposite. A challenge I always felt for that theory was, how do you explain the goal gradient effect? I created a computation with my control theory approach. I created 4 computational models. 3 of them were variations in the control theory approach. 1 of them was a different thing altogether. At the end of that, 2 were eliminated, 2 of the control theory ones. There's 1 control theory one left, and the other explanation is still left. And what I have to do, I haven't gotten around to doing this, is figure out a design that teases these 2 apart. It provides a process explanation using that previously structured, one of them, using that previously structured, mentioned structure. So I'm able to explain this, but I also have another explanation, so my next job is to pit those against each other. Get red 2. Ballard et al., we modeled avoidance goals either as positive or negative feedback loops in multi-goal settings. So if you, in multi-goal context, so positive feedback loop is what Carver and Shire always argue is going on. That version turned out to be ill-behaved in some configurations, whereas the negative feedback loop was much better behaved. So we had the ability to say that same structure actually can work for these kinds of avoidance goals too. Another one with Ballard that's just gotten pressed. We pitted 2 processes. There's 2 processes usually explain why deadlines can enhance motivation. So those earlier models I showed were ones where the deadline was the same, and we never had the challenge of worrying about when deadlines are different. The empirical literature is pretty clear that as a deadline approaches, you're much more likely to work on that goal compared to another one where the deadline's later on. Why is that? Turns out there's 2 explanations for that. We were trying to incorporate that into our model, and both processes appear to be involved. This involved 3 different experiments that would be able to tease apart these processes. It's not very complicated computationally for the human mind. Whether people can read it and find it complicated or not, it's up to them. I am going to show you this one. This one to me, I mean, again, this is just beautiful. Those agents you saw before, I've gotten rid of the boxes inside those rounded boxes, and so there are many of the same agents. What makes this beautiful here is there's signals coming out of some of this agent, particularly this agent here. And in the original model, this one signal just went to this agent. Now the signal goes to these 2 functions as well as that agent, and this function represents a time pressure explanation, and this function represents a hyperbolic temporal discounting function. Turns out both of them are necessary to predict choice in this case. It's a beautiful, elegant, it's not hard to believe the human mind is doing this, and it's this example of our balancing the things we need to worry about in order to get around in life. I just love this model. Identifying methodological and theoretical challenges. So Hanisch, on why methods of measuring organizational withdrawal processes were fruitless, that was like one of the first computational models in the OB field. Hint, small effects problem was the issue. One of my students, Bay, showed how mediation and moderation conceptualizations are inadequate when considering dynamic processes. I wanted to show you that one, but I know I don't have enough time. But the model on how trust develops, pretty cool model. We're working on that paper. Another student of mine, Halper, and I showed how sequential, recursive, causal path models are probably underspecified, probably not a surprise to most of the people in this audience. But we're going on to argue that the path modeling approach constrains our thinking as well as our empirical work. They require that all the constructs that are in the model be measured, discouraging representation of latent underlying processes. That's a big problem. They rarely capture the system with these in which processes are interested or embedded. So what we're doing is we're playing off of this path model Colquitt et al. Published in 2011, and saying, so this is about how trust eventually affects job performance, and they measured all these things at time 1 and this thing at time 2, and so they said this, we can't reverse that, we can't have that after. Yeah, oh, really? Here is the computational model where what we're saying here is the supervisor is doing things which will create a perceptions of employee treatment and will come back and affect their motivation and their performance, and these things will come back and affect the way that the supervisor treats them. And so I've got a supervisor, I've got an employee, I've got peers, I've got some other contextual variables. I'm trying to have some fidelity in terms of representing the system. I've got feedback loops in here. So what I'm doing is I'm taking the abstract that Rich Bettis showed us yesterday. Here's an example of it. And trying to see whether that could really be maybe what's going on. Here is the results of running that model. The important thing here is the variables they go to an asymptote. They get stable. It seems like this is a possible working model. I've been playing around with the parameters. It turns out it's ill-behaved regarding some of the parameters, suggesting to me I am not capturing this very well because people aren't. Well, actually, I am at the point. I'm thinking, are people this ill-behaved? Do people really do with this model? This is one of the times when you go, so is this model making a prediction that seems surprising, but maybe we should go out and find out it's true, or do I have a bad model and I'm not sure where I am on this model yet? Identifying methodological challenge, and about this, when the data are dynamic, and so our larger point with this paper right now is this beats path modeling. And particularly when the data are dynamic, researchers have, have they thought through correctly, it turns out also it's very cumbersome to represent. So one of the things is the quant people out there are going, we can use SEM and path models for doing latent longitudinal data. I don't need no stinking computational model. And what we're arguing here in this paper is, yeah, but to represent it, this is what one variable looks like represented in a latent SEM path model for a variable that's going to be in a longitudinal study. That's what it looks like. Here's with some of this taken away, and then here's two variables. And the idea here is y has got some autocorrelation, and x has got some autocorrelation, and then they're related to each other at some, and we're going to be, and I'm not saying this is wrong. What I'm saying is as a way to communicate the theory, this is not going to help. This is what that model looks like in a computational model. Maybe, if I want, I'm going to say, well, x is a level variable, and that's how I might signify that x is a level variable. By the way, so what does that mean, x is a level variable? Well, a level variable is a variable with inertia, or the conservation principle. It holds its level until moved by something. And that is what creates autocorrelation. If this has that property, y will look that way. It will also have autocorrelation. But y may not have that property. Knowing what variables have the property of conservation and what don't is one of the ways physics made boatloads of progress. We need to understand which variables have this kind and which don't. If I look at a statistical model, they all have autocorrelation, but I'm not sure the source of it. Longitudinal designs often add little validity, but much perception of validity. The order of measurement matters little when the system is in homeostasis. Likewise, examining change can be of little use or misinterpreted without control over perturbations in the system. Repeated measurements of systems in flux may not really be what you think they are. So a big popular thing these days is experimental sampling methodology. We have a computational model that shows how it's not necessarily going to be diagnostic. We have a student who has a recent one here on vigor and OCB. OCBs, what motivated this was there's two papers that used ESM to look at the relationship between vigor and OCBs, and one of them said they're going to be negatively related, and they found that, and another one said they're going to be positively related, and they found that. So how do we possibly explain this? Well, here is a computational model of what might be going on. This is a pretty simple model, and I'm also thinking actually this is pretty general. The idea here is there's some sort of resource, in this case an energy resource, and that resource determines how much vigor you can have. At the beginning of the day, the level of that resource is a function of sleep quality, and as the day goes along, you're going to have more or less vigor, and as you have vigor, that's going to deplete your resource. And you might have more vigor when you have social interaction, which you'll do if you're doing OCBs, and less if you're not doing OCBs. That's the model. This is the results of running that model. So over the course of a day, here's how vigor changes. And this is the case when there's no OCBs. I'm now, oh, by the way, that's what it looks like if you look at physiological data about what happens with vigor over the day. So we kind of match that. That wasn't our model produced that. We got our model to produce that. Okay. So this is what happens when I have vigor in the model. Energy resources with and without OCBs have that pattern. If I measure my ESM measures at the end of the workday, then it looks like I have more vigor when I have OCBs. If it's when they get home just after the end of the workday, then it's the other way around. If you don't know what's going on and you say, oh, I'm going to collect this over time, over days, and this time I'm going to choose to do it here, and then some other time I choose to do it there, it's going to make a difference. Paradoxes versus harmonies. So in the model I showed you before, we showed why relative discrepancy from a goal could positively and negatively relate to goal choice. The Ballard et al. Shows why deadlines can enhance and reduce motivation to pursue a goal. Vancouver, Teminani, and Yoder showed why information seeking might positively and negatively relate to role clarity. Colton showed why engaging in OCBs might positively and negatively relate to subsequent vigor. Vancouver and Pearl showed why self-efficacy can positively and negatively relate to persistence and why the mechanism is normative. Beautiful things. I think they're beautiful. Implementation. So this is what maybe one can do. We haven't really done this, but in the right now I'm working on a project with a woman named Ping, and we're looking at that justice model, and we're trying to optimize the parameters to figure out what's the best way to get the most trust, performance, and respect among these people, among a set of employees, which might be something one could do if we had evidence that the model was correct, which I'm not willing to say we're there yet. We had that model on performance to maximize performance over time in jobs as a function of job complexity. One can use that to figure out how should we be selecting, training, how do we optimize that. The Vancouver and Pearl can use the model to optimize good persistent decisions if we've represented the task properly, maybe. I don't do that yet, but the idea here is in the end, you get these models and you can optimize them and say, oh, let's go in the organization. We now know what's the best thing to do according to that model. The scientist's job is to develop and critique theory. We use logic, we use data. The more rigorous the logic and data, the more valid the theory or criticisms are likely to be. Hypothesizing should facilitate diagnosing, challenging the theory, because they are unique to the theory and the arguments. They do not follow from other theories or explanations. I don't care whether you harked it I don't care whether you thought of it before or after. If I have a data set that is diagnostic regarding a theory, and by diagnostic I mean there aren't other explanations for this effect that you found, I don't care the order with which that happened. What I want, and this goes to Jason's things, it would be really good if I designed a study that had that property, and if I think about it ahead of time, I'm much more likely to do that. So that's, I think, Jason's point. Strategically hypothesizing, much better than hypothesizing after the fact. But sometimes you might do it after the fact, and that gets us to an issue of whether we like that or not. Typically, the issue of doing it ahead of time, we think the only thing we worry about usually is the alternative explanation is chance. Okay, I'm sorry, statisticians, they have dominated this world. I am much more worried about all the other explanations. Statistics, that's cool, and you really got this great system. That's just one alternative explanation, chance. But there's all these other explanations, and we need to really be worrying about those things. Let's assume, yet we assume that finding a reliable effect is explained by one theory tested. So one of the other things we do all the time is we say, here's my theory. I therefore make this prediction. I find this prediction. Therefore the theory is correct. That's modus tollens. It's confirming the consequence. That is not a valid argument. I have done it. I will do it some more. It's hard not to do it, but it's a weak argument. And that, by the way, is they do that all the time in a non-hard, my theory makes this prediction. It's still weak, whether it was done before or after. We should be evaluating the quality of the theory and the quality of the design to eliminate alternative explanations. We should not worry about the order. I think the idea of worrying about the order, it's balderdash. It is well known verification of a prediction may carry very little inferential power back to the generating hypothesis. I don't know why I started. I'm harping on Harking. I'm not quite sure why I got there. But I basically feel it's irrelevant for most things we're worrying about. What we really need to be worrying about is just good science. I will tell you the story about why I think this way. I spent a lot of my career, and I've got my bones, challenging self-efficacy. Self-efficacy was this well-established theory. Everybody was writing papers saying, we predict self-efficacy is causally going to relate to performance, i.e. self-efficacy causes performance. Though, okay, we're not really going to have the design to be able to say causes, but there's this theory out there that that's going to relate to performance. And apparently people didn't think, wait a minute, so self-efficacy is essentially a self-report of ability, and we know ability relates to performance, so who cares that self-efficacy relates to performance unless we can say self-efficacy causes performance, and your designs don't allow us to say that, even though you had the theory and you said it beforehand. I don't care. It was dumb theory. It was dumb studies. Now, just to be clear, self-efficacy can positively relate to performance in some context. It's much more complicated than a simple relationship. But my point is, I am looking at the nature of the theory and the data and worrying about alternative explanations. I don't care the order with which they came up. In fact, what I tell my students is, when you're reading a paper and you say, I wonder if they thought of that, if they really thought of that ahead of time. Well, then say, what if they didn't think of that ahead of time? Would that make a difference? And if you say, yeah, that means the study would be stupid, and you say, okay, now let's say they thought of it ahead of time. Is the study still not stupid? Oh, yeah, no, it's still not. It's still stupid. Yeah, you're right. It doesn't matter the order. So the game here is usually to identify the explanations or the theory and whether or not they exist. It's not to see whether some effect is replicable, because everything's related to everything. And I'm saying damn you, Daryl Bem, because there's certain kind of questions. Is there ESP or not? That is there this relationship? And that was, yeah, what he did, hiding, harking, that's why he found it. So there are cases where it's a real problem. It's like an urban myth. There's some truth to the worrying about harking. But it depends on your question. It's the quality of the theory and the diagnosticity of the design that matters. Computational models can help us assess the quality of theory and make it better. Computational models can confirm or generate the theory's predictions. Computational models of alternative explanations can be generated to improve the diagnosticity of designs by identifying unique predictions. Computational models can be used to determine what statistical or other analysis will facilitate theory testing and what designs and analysis are useful. Bottom line, the order of hypothesizing results are not nearly as important as the order of causal processes and the ability of hypotheses designs to challenge theory. It's the diagnostic value of the design and the quality of the theory that matters. And I kept going. I had scapegoat, and then I have red herring, urban myth. I wasn't quite sure what graph to go with, but I am done. Stronger than I know.
Thanks. I have a question about hurdles of computational modeling when you have multiple model choices. You're doing model selection, and you see models that are different, might be contradictory, and they still have a good fit. And so how these affect interpretability and theory validation, and how you can also combine multiple models in an ensemble that could actually improve your fit but decrease interpretability.
Okay, so you're of course asking a relatively sophisticated question because I know you do this kind of modeling. I mean, so the answer to the first part of your question is I like what Forrester said in math modeling in 2000, which is the best way to validate a model is the hypothesis test, which is to say this model makes this prediction. Now let's go see if that prediction is true. And in particular, if you're in the idea of this model makes this prediction and that model makes that prediction, I have two computational models. Can I use them to figure out how I can see their difference? Does that give me clues about what design elements that I can employ that they would create different predictions, which can be a challenge, but that's hopefully the first thing you can do and the best thing you can do. The idea that, because the idea here is I'm going to have, here I have two models that fit a certain data set, so I therefore have two plausible explanations. Which one is right? And the answer could be, well, only one of them I need, and I can tease that apart. But the third answer is well, it turns out maybe they're both right. So we did the one where time pressure and hyperbolic discounting are two explanations for why it is people are more motivated as the time comes. And it turns out both of them are going on. And so that's, I don't know if it's cascaded, but that's where it turns out both of them seem to be working out. But I mean, the fundamental challenge that you're describing, I think, is the fundamental challenge that most experimentalists have to deal with, which is how do I get at what is the right thing going? Well, how do I get at what's the underlying process? And a model isn't necessarily going to solve that problem. It's still the challenge of, okay, now how do I get at this empirically to be able to find out what's right or wrong? The most complicated thing you're describing is the issue of generalizability versus number of parameters. So the more parameters there are, the less generalizable it is, because you have to estimate those parameters. If they're free, you have to estimate them, and therefore I can't use them to predict some new situation because I have to estimate what's going on in that new situation. We'd rather have models that have fewer parameters than more. Sure.
Right.
Is that what you're getting at?
Okay, Jeff, thanks. That was great. So I agree with many of your points, but the one thing I think you're missing, you might be missing, I'll just let you respond, is that I think it's not about whether a finding can be of use, whether I anticipated it before or I interpreted it after. It's the idea that some people are pretending that they anticipated it before. I can't think, maybe you can give me one, but I can't think of any other situation in science where we would say it is okay to pretend that you did something when you really didn't do it.
Okay, so I have two answers to that.
Okay.
Answer number one is, it isn't about you. You're not making this prediction. This theory is making this prediction. So when you write it up and you say, this theory makes this prediction, that I thought of this theory beforehand or not isn't what you write, because I don't want you to lie. It's about the theory. Now, the second answer to the question is the more empirical one, which is, yeah, well, but people, they are more impressed by the idea that it was predicted ahead of time or not, and will that be a good or a bad thing? And that's where it gets empirical, because one answer could be is, well, if it looked like it was done after the fact, then I don't believe anything about it. And what I'm trying to argue here is, well, look at the diagnosticity of the methods and the logic of the theory. And that's, so going back to the example, that student, the sinner student, if it turned out the theory that they created was brilliant, well, then it was brilliant. And if it was stupid, hopefully we figured that out when we were reviewers. I don't know if that last part.
Okay, but then to solve the problem, we just rewrite the introduction section by saying if.
Okay, now I'll say a third thing,
Correct.
which is,
If we adopted this particular theory, this
Yes.
is what we would
Okay.
predict.
right.
And that would be different than saying, I predict that.
Yeah, I'd say, don't say I predict that. Say if this theory is correct, it makes this prediction. If we adopt this theory, that's right. Now, there is an issue of capitalization on chance, which for certain kinds of designs and certain kinds of problems makes it so you better damn well come clean regarding the order of this. The issue of predicting who's going to be president, for instance, you're like, yeah, no, that's a context where you could be capitalizing the crap out of chance, and therefore you better be upfront about it. Other contexts, the likelihood you're capitalizing chance are really, really small. My effect size is 0.0001. I'm not sorry. Boy, that was a bad mistake. Not my effect size, my p-value. You're not capitalizing on chance. You don't need to worry about that. So context matters for whether you should worry about harking it.
Okay.